Hi everyone, in this video we are going to look at rate of reaction. As the name suggests, it has to do with a time and how fast a chemical reaction is happening. So just a definition of rate of reaction. Rate of reaction is a measure of how fast a reaction takes place. And before we move on, it's important for us to write rate of reaction instead of speed of reaction. Now when we want to talk about rate of reaction, the first thing we want to do is to measure rate of reaction. For any chemical reaction, it is standard that reactants are being converted to products, and this is where we can measure rate of reaction. During a chemical reaction, the reactants slowly decrease and the products it will increase slowly. So we can measure how fast the reactants are decreasing and how fast the products are being produced. So there are a few aspects to look at, and there are a few units that we can measure or quantity. Volume of gas produced, change in mass, usually for reactants, and the formation of precipitate, which will give us color change. Right? So based on these three quantities, we have different units for rate of reaction. For volume, it will be volume per time. For mass, it will be mass per time. If it's for precipitate, there will be no units because color cannot be quantified, so it's just per time. Let's look at an example of a chemical reaction. For this example, it is a reaction of acid with metal carbonate, whereby salt, water, and carbon dioxide is produced. For this chemical reaction, there are two ways to measure the rate of reaction. First is to measure the mass reduced and the volume produced. So let's start with measuring the volume. To collect gas, we use this method called downward water displacement method. We can use a burette to collect the gas, or we can use a measuring cylinder to collect the gas. So as time goes by, this volume of gas will increase and the water level will reduce. And when we tabulate the results, we can draw a graph and it will show a curve like this. As the time increases, the volume of gas collected increases, and it will go until a certain point that the graph will remain constant because the reaction is completed at this point. We can also collect gas using another method, using gas syringe. That's one way. So for measuring mass, we can put the conical flask together with the acid solution and calcium carbonate on a digital balance. We use a cotton wool just to prevent the spill of the solutions, and we can expect to see a graph like this. At the beginning, the mass reduces drastically and it slows down at the middle, and at the end it stays constant because the reaction is completed at this point. The graph shows this form because calcium carbonate is usually used in excess for chemical reaction like this. So instead of touching 0, it remains constant above 0. Now let's look at these two graphs in detail. We want to look at the rate of reaction by just looking at the shape of the curve. We want to look at the gradient of the curve at different points. So let's start with the starting point. We draw a triangle to show the tangent or the gradient. As we can see, the gradient is very steep at the beginning. That shows the rate of reaction is very high at the beginning. So at the middle, the rate of reaction decreases, or the gradient decreases, and it decreases even more later on. And lastly, it stays constant, whereby the rate of reaction is 0. So when we draw a graph of rate of reaction against time, we'll find that as the time goes by or time increases, the rate of reaction will decrease. And there's we can formulate a relationship between rate of reaction versus time. We can say rate of reaction is inversely proportional to time, or we can say rate of reaction is directly proportional to 1 over time. So if we draw a graph of rate of reaction against 1 over time, we will get a straight line, directly proportional straight line. So that's all for today's lesson on rate of reaction, how we measure rate of reaction, and some of the graphs involving rate of reaction.